You know that feeling, right? You tap your phone and boom, the app just opens. Or your game controller buzzes the exact second you get hit. It seriously feels like magic. But it's not. It's actually this incredibly clever idea in computing called an interrupt. And today, we're going to pull back the curtain and see exactly how it all works.
So seriously, how does that happen? It's not like your controller is just constantly bugging the game, right? Like, hey, am I hit yet? What about now? Now? That would be a colossal waste of processing power. No, there's a much smarter way to do it. Think of it like a digital reflex, something that just kicks in at the perfect moment.
Okay, so to really get how this digital reflex works, we've got to look at what's basically the nervous system of our devices. And it all boils down to one very special kind of signal.
And that signal is called a hardware interrupt. The best way to think about it, it's literally a fire alarm for the processor. It's this high-priority electrical signal that basically screams, drop everything you're doing, this is an emergency. This is how a system deals with all those things that just happen, things that don't follow a neat little schedule. We call those asynchronous events.
So what kind of events are we talking about here? Well, they're happening constantly, right under our noses. A simple timer expiring, you pressing a button on your mouse, or even a little bit of data arriving from your Wi-Fi router. Every single one of these things triggers an interrupt that demands the processor stop what it's doing and pay attention right now.
And here's the thing about an interrupt. It doesn't wait in line, it doesn't take a number. No, it shoves its way right to the front of the queue because, as far as the system is concerned, it is the most important thing happening in that exact moment. I mean, look at this. In the processor's world, the hardware interrupt is king. It has absolute total priority over any and all software tasks. Doesn't matter how important they seem, it is the top of the food chain, period.
So when one of these interrupts arrives, the processor literally drops what it's doing and immediately jumps to a special little piece of code that's designed to handle that specific interrupt. This code has a name. It's called an interrupt service routine, or ISR for short. You can think of it as the processor's pre-written emergency action plan.
But all this power, it creates a pretty big problem. What happens when this super-fast, high-priority ISR needs to talk to the normal, slower software that it just rudely interrupted? How do they share information without stepping on each other's toes and creating total chaos? Okay, so picture this. We've got a normal software task, just chugging along, doing its job. It's in the middle of updating a shared counter, and right now, the value of that counter is 19. Everything is fine. Everything is orderly. And then bam, an interrupt hits. The ISR that runs also needs to change that counter, so it bumps it up to 20. Now, when control goes back to the original task, it has no idea what just happened. It's still thinking the value is 19. It's working with old, stale information, and that can lead to all sorts of data corruption. This classic problem is called a race condition, where two different things are racing to change the same piece of data, and the result is, well, it's a mess. So, how do we fix this mess? Well, the very first step is to give the compiler a heads up. We use a special keyword, volatile, which is basically like putting a giant warning label on a variable. It tells the compiler, hey, this variable's value can change at any time, completely out of the blue, so don't you dare try to get clever and optimize it away. Every single time you need it, you read it fresh from memory. This stops the compiler from making bad assumptions that can lead to really nasty bugs.
But just warning, the compiler isn't quite enough. We also have to actively protect the exact moments when we're reading or writing that shared data. And the most straightforward way to do this is by creating something called a critical section.
The process itself is pretty simple, in theory. Right before you touch that shared data, you temporarily disable all other interrupts. That's the lock. Then you quickly make your change. And then you immediately re-enable them. That's the unlock. Now this whole operation has to be lightning fast. Why? Because while those interrupts are disabled, your system is effectively blind and deaf to the outside world. Think about your car's anti-lock brakes, or a heart monitor in a hospital. A missed interrupt in those systems? Yeah, that could be absolutely catastrophic. So yeah, disabling interrupts works, but it's a bit like using a sledgehammer to crack a nut. It's a brute force solution. Thankfully, there's a much more elegant and refined way to handle this: a synchronized handoff. Think of it like a perfectly executed relay race for data. This design pattern is called a deferred interrupt, and the whole philosophy behind it is to keep that interrupt service routine, the ISR, as short and as fast as humanly possible. The ISR does the absolute bare minimum, like maybe it just grabs a new reading from a sensor. And then it defers, or hands off all the heavy, time-consuming processing to a dedicated, regular software task.
So how does it actually do this handoff? Well, it often uses a special signaling tool called a semaphore. A semaphore is really just a simple way for one part of the system to signal another. The analogy of a flagman at a construction site is perfect. It's just a little flag that tells a waiting task, okay, the coast is clear, you can go now.
Let's walk through how this works in action. First, a high-priority software task basically puts itself to sleep. It's just blocked, waiting for that semaphore signal. It's not wasting any CPU cycles. It's just waiting. Then the hardware interrupt fires. Its super-fast ISR runs, grabs whatever data it needs, and then gives the semaphore. And finally, the instant that semaphore is given, the waiting task immediately wakes up and gets to work processing that new data. It's just a clean, super efficient, and perfectly synchronized handoff.
So, when you put all of these pieces together, the incredible priority of the interrupts and these really clever communication patterns, what you get is the very foundation for building truly responsive, real-time systems.
And this leads to a really common and powerful design pattern that you see in tons of real-time systems. You'll have a tiny, fast ISR that just samples data, maybe from an analog to digital converter. It signals a high-priority task which does the complex number crunching, like a fast Fourier transform. And all the while, a much lower priority task is just handling things like user input and updating the display. It's really like a beautiful coordinated dance between tasks, and it's all orchestrated by interrupts.
So next time you tap a screen or feel that rumble in your controller and it feels instantaneous, just take a second. Think about it. What invisible, high-speed handoff just took place under the hood to make that happen? It's not magic. It's the elegant and powerful dance of the hardware interrupt, the silent hero that makes it all possible.